Greetings all. We're going to cover chapter 11 rather quickly because there's a lot of things in this chapter that you've had in chemistry. The terminology may sound a little bit different, more physics-like as opposed to chemistry-like, but the ideas are very much the same. We already talked about the important concept of thermal contact, that anytime gases, liquids, solids come in contact with each other, heat will go from the hotter to the colder, the net heat. The net heat will never go the other direction. That's kind of like the zeroth law of thermodynamics. And one of the people instrumental in helping us to understand that the discussion of heat energy belongs in physics and in fact is connected to mechanical energy directly is James Prescott Joule. James Prescott Joule, you can see, lived to be about 70. He grew up in a family with 4 siblings, and he had very poor health. He had a bad back, and he also worked in the family business, which was the brewery, and he learned an awful lot about machines and temperature and things like that there. He also became a Christian, especially from his reading and knowing about John Dalton, who was a few years before him. In fact, here is a quote by James Prescott Joule. "It is evident that an acquaintance with natural laws means no less than acquaintance with the mind of God therein expressed." So James Prescott Joule recognized that laws are something formulated by a mind. And so the laws that we discovered, or we discover with our minds, are the product of a mind that put them there. And that mind, of course, is the Creator, God Himself. In other words, if there are laws, there must be a lawgiver. One of the concepts that we didn't talk too much about in chemistry is the idea of internal energy. Anything that is made out of particles, be they atoms or molecules or ions, which are the principal particles you studied in chemistry, means that those particles do not have zero motion because they would not be at 0 Kelvin. So because they have some kind of motion, they must have some kind of energy. And typically in gases, we think of particles being able to move linearly until they collide with something or the interior of the container that they're in. They can also move rotationally, but as far as vibrationally is concerned, we associate that more with the particles that make up a solid and are held in some type of crystal lattice structure. We also need to recognize that besides this kinetic energy, you have the potential energy stored in the bonds between the particles. And so if you think back to chemistry of all the van der Waals forces, and sometimes those forces are dipole, or the London forces, which we call dispersion interaction forces, or the special dipole forces, which we call hydrogen bonds. All those bonds represent a kind of potential energy stored in that bond. We also have a very important definition of the word heat. Heat is not something we measure directly, but heat is something that we measure by what it does when it is transferred from one place to another. When heat is transferred, it does one of two things. It either causes the temperature to change, or it causes a change in state, which is something that will be covered later in this chapter. So the transfer of heat, which means the warmer substance is going to lose a certain amount of heat to the colder substance until they become the same temperature. And that means that the heat lost must equal the heat gained. heat lost equals the heat gained, which is another way of talking about the law of conservation of energy, specifically heat energy in this case. And this little identity will become the basis for a lot of the math problems in this chapter. Now, as far as units of heat are concerned, we typically use the joule, but in the United States and historically, we often use the word calorie. And a calorie has a specific definition. It's the amount of heat it takes to cause a temperature change, particularly a temperature change of 1 degree for 1 gram of water. 1 calorie is the amount of heat it takes to raise the temperature of 1 gram of water 1 degree Celsius, and specifically this temperature right there. We, of course, now more and more, as science has moved on in the last 50 years, and as I have observed in my teaching, use the calorie less and less and use the joule more and more. And here's the identity for going back and forth between the two. 1 calorie equals 4.186 joules. And you might remember that this is the mechanical equivalent of heat. In the lab that we did with the big long tube 5 feet high or taller, and with the buckshot falling 100 times the length of the tube, our goal was to see how close we could come to 4.186 as our mechanical equivalent of heat. And here we have a student who is going to be lifting weights, and this student is very concerned about the fact that he has just had a bowl of cereal and milk and has consumed 320 calories. Notice that calories is capital C. Capital C means a kilocalorie, or 1,000 calories. And that's the way in which it is spelled on cereal boxes and on other boxes containing food and candy bars, wrappers, and so forth. It's with the capital C. So if you're having a piece of chocolate cake, that's 70 calories. For the physicist, that's 70,000 calories that would then need to be converted into joules. Not that that should ever make you think twice about eating a nice piece of chocolate cake. In fact, I think chocolate cake makes a very good Christmas present. In any case, what we're going to do is equate this 320 calories of heat energy and see how much potential energy from lifting the weights up and down is necessary to offset it. So the first thing we do right here is to convert our calories into regular calories and then into joules. And then we take that number and we set it equal to the potential energy. Now the potential energy is mgh, but you've got to multiply by 2 because you're lifting the weights down, and there's a resistance against your muscles, and then you're lifting them back up again. And then, of course, you're doing it n number of repetitions. And our goal is to find out how many repetitions of up and down it takes. And so you can see it takes just a mere 6,840 curls with the barbell to completely cancel out the 320 joules of energy, calories, capital C calories of energy represented by the bowl of cereal and milk. Of course, when you eat food, a lot of that energy goes to maintaining your body temperature, as well as your heart beating and everything else that your body does that requires energy. Now we move on to the concept of specific heat. You might recall from chemistry, we kept talking about Q equals mc delta T. And in physics, we have a tendency to use capital Q instead of lowercase q. Typically, our Q now is in joules, whereas In past decades, I recall Q was always in calories. In any case, if you can imagine getting out a plate after a Thanksgiving dinner a few days later, and you put a bunch of leftovers on it, a couple pieces of turkey, maybe a big dollop of mashed potatoes or sweet potatoes, maybe some green peas, maybe a chunk of cornbread or something like that, and sticking it in the microwave. And then you heat it up, and then you take it out. Well, very, very quickly you will notice that some of the foods cool down much more rapidly, meaning they lose their heat to the kitchen, and some of the foods do not cool down as rapidly, even if you had the same mass of every single kind of food. Now, of course, part of that reason would be surface area. The sweet peas, for example, would have a much greater surface area through which heat could be lost than perhaps the mashed potatoes. But it's also because each of the different foods has a different specific heat. So Q equals mc delta T. C is the specific heat. And you can see an example of lots of different specific heats in this chart. Normally, we would do a lab on specific heats where you would have 3 different kinds of metals, 3 blocks of metal that you would heat up in boiling water and then transfer them to a calorimeter where the hot metal would lose its heat to the water and the water temperature would go up. And you would do this lab in order to calculate the specific heat of each metal. Sadly, we don't have time to do that this year, but it is a pretty simple lab, and you'll have a math problem or two that will cover that ground in any case. So the specific heat then could be said to be defined as the amount of heat divided by the mass times the change in temperature, which, remember, delta T can be either Celsius or Kelvin. And again, here is your mechanical equivalent of heat when you want to convert joules to calories, for example. It also happens to be, if you look over here, the specific heat of water. If we were talking about the specific heat in terms of grams instead of joules, the specific heat for water would be 1, as you can see right there. And here's the formula that you'll be using in your homework, as well as on an upcoming test in the not-so-distant future. Now, because things have different specific heats, there are an awful lot of meteorological phenomenon that you can explain. For example, when you are at the beach, the specific heat of sand is very, very low. And by comparison, the specific heat of water is very high. In fact, just about anything has a lower specific heat than water. It's one of the remarkable properties of water that is absolutely mind-boggling and absolutely essential, not only for there to be life, but for there to be a habitable planet for that life. And books have been written about all of the amazing properties of water, like hydrogen bonding and its high specific heat, and the hydrogen bonding that causes high melting and boiling points. And I've read one of those books, written by a non-Christian who just gushed over how incredibly well designed the water molecule is. And he was ever so close, but just could not pull the string, and then recognize that if it's designed to such a high level of precision and complexity, there must be a designer. Maybe that'll happen someday. He's a world famous scientist, and he's getting closer and closer to the truth. In any case, because the sand has a lower specific heat, it reaches the temperature of the air very quickly. It takes a while for water to reach the temperature of the air because it absorbs so much heat. Now, That means that once the beach has reached the temperature of the air, all the heat is going to rise. And of course, if you're sitting there on the beach and all the hot air is rising, you'll notice something. You do not suffocate when the air rises and leaves you. And the reason, of course, is because the air over the water flows in to take the place. And another way of saying it, it's going from a high pressure to the low pressure caused by the rising warm air. We call that wind or breeze. And so you feel the breeze when you're at the beach coming in off the water, and it's refreshing, and it makes it comfortable to be on the beach, even if the sand is hot. However, you do not want to go out on a raft. You do not want to go out on a raft, and here's somebody on a raft with his head over here, and there's his feet sticking up, and fall asleep as the sun sets. Because here is what will happen. As the sun sets, then everything gets reversed. The beach with the low specific heat cools down very rapidly, and the water with the high specific heat warms up very quickly. Cools down much more slowly, so that the water is warmer than the beach. So the warm air starts rising over the water, and that means that the cooler air from the land flows to take its place, which means the person on the raft who's fallen asleep begins to drift out to sea. And this is when you hope the Coast Guard is nearby. But of course, these wind currents are much more important in terms of regulating and moderating the temperatures of the planet, especially near bodies of water, so that the temperatures don't get nearly as extreme as they otherwise could farther inland. It's one of the reasons why millions and millions and millions of people prefer to live along the coasts. We also have the phenomenon of thermals. This can be air, this can be water. And if you ever have watched eagles and vultures and hawks soar, they're finding a thermal, a mass of warm air surrounded by cooler air. And as that mass of warm air rises, they just float upwards on it and gain some altitude. And then they can look down and spot some animal somewhere that isn't aware that they're around and swoop down and get it. I've been on cliffs and mountains before where I've been, in a sense, at eye level, the same altitude as the eagle or the hawk, and they are fascinating to watch. So in this particular math problem here, we have a steel strut, which would be like a girder, a piece of metal. It's near a ship's furnace, and it gives you its length, and it gives you its mass, it gives you its cross-sectional area, and it tells you it absorbs a whole bunch of joules, okay? About 250,000 worth of joules of heat energy. And if we come up here to this problem, you can see that the first thing we can do is calculate the change in temperature of that steel strut by solving for delta T. Remember, this is the change in temperature. If you happen to know the initial temperature, you would have to add the change in temperature to the initial temperature to get the final temperature. Make sure you distinguish between delta T and the actual T. Once you know the change in temperature, you can bring that number down here and plug it into the equation, which you did in lab, I think it was 16, the coefficient of linear expansion, and find out how much that girder is going to lengthen. And then once you know that, you can plug that down into the Young's modulus, and you can solve for the strain, the pressure, the force per unit area that strut is going to feel as experience as a result of that increased length. And I would remind you that one of the most common mistakes that's often made, and not that doesn't happen in this problem, but finding the cross-sectional area is where students often make mistakes. All right, I'm going to stop right there for the time being, and I'll record another screencast, but this is a good stopping place.